Hello, today we're going to review Unit 5 for the AP Chemistry exam. It's all about kinetics. So we have our first free response question here. We have an unknown gas reacts with fluorine to form DF4, and then we have experimental trials to determine the rate law expression for the reaction. And then it says the student claims that the reaction is first order with respect to D, and do you agree or disagree? So when you have these multiple trials, I want to find with respect to D, so that means I need to pick two trials where the other reactant is the same. So I want to look at trials 1 and 2 because the F2 is the same and won't affect the overall reaction. So for D, the pressure is doubling, and you can see that the rate is also doubling. So because it has the same effect on both the pressure and the rate, then it is first order. So you would say, yes, I agree. As you can see in trial 1 and 2, as the pressure doubles, the rate also doubles. And that would be enough. And that's 1 point only for that one. Okay, so now it says, what is the initial rate of disappearance of F2 in trial 1? And justify your answer. I'm going to go ahead and write down the balanced chemical equation here. So they gave you this equation. I just didn't copy it over to the slide. Now you can see that this column here is the rate of appearance of DF4. And it says, what is the rate of disappearance of F2 in trial 1? I'm going to use stoichiometry to figure this out. And that's for DF4. For every one DF4, there are 2 F2 that are used up. So you would multiply by 2, you get 5.00. Weird looking 5 times 10 to the negative 2. So it says, what is the rate of disappearance? I would say it disappears 5 times 10 to the negative 2 torr per minute. If it said rate of change instead of rate of disappearance, I would say that it would be negative 5 times 10 to the negative 2 because you're using up the F2 over time. But since it said rate of disappearance, I think it's more appropriate to use the absolute value there to show you that's how many torr per minute are used up. Okay. And that one was just 1 point. For part C, a student claims that if element D is in group 18, then the molecular geometry of DF4 is tetrahedral, and do you agree or disagree? So this goes back to Unit 2. If it's in group 18, then it's a noble gas. That means it has 8 valence electrons. So I have 8 from the D, and then fluorine has 7 valence electrons. And 7 times 4 is 28. So total, I would have 36 valence electrons. If I put D in the middle, and then F around the outside, I just made 4 bonds, which is 8 electrons, so 28 is left over, and I need to add those on to the outermost elements first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28. Because there's extra, once you fill out the outermost atoms, then you start to put those on the inner atom. And so those extra 4 electrons go on the inner atom. Now, because it has 4 bonds and 2 lone pairs, it is not tetrahedral. Tetrahedral happens when you have just 4 areas of bonding around the central atom. So it's not tetrahedral. You'd say, no, I disagree with the student because there's 4 areas of bonding and 2 lone pairs. It would be square planar. You didn't have to say for sure that it was square planar, but you needed to mention that those lone pairs make it not tetrahedral. And that one was 1 point as well. Okay, so now this time we have the same reaction. I'm going to go ahead and write the balanced equation again. Okay, moles of particles present in the container after D and F2 have reacted in a different experiment. Each particle represents 1 mole of their respective substance, and the box corresponding to before a reaction is intentionally left blank. For part D, if the total pressure at the end is 12 atm, what is the partial pressure of DF4? So this is a Dalton's law question. So if it's 12 total, let's go ahead and count our particles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 DF4 molecules. And I have 1, 2, 3, 4, 5 F2 molecules. So that means I have 15 total molecules at the end of the reaction. So that's kind of our mole fraction, right? 10 to 15 for DF4 multiplied by that 12 ATM total. And I get my partial pressure for the DF4. 10 divided by 15 times 12 is 8. 8 ATM is my partial pressure for DF4. That was 1 point. Then it says, assuming that only D and F2 are present in the container before the reaction, determine the number of moles of D and F2 that were present in the initial mixture. So this is a stoichiometry question, really. All of the D atoms were completely used up because there's none after the reaction is complete. So D is our limiting reactant. F2 is our excess reactant. And then DF4 is just the product. So I need to make sure that I have the same number of atoms on both sides. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means I must have started with 10 of the D atoms to begin with. And then for F2, I know that I have 5 F2 molecules for sure, but I also have the ones that became part of DF4. So I would have 25 F2 molecules to begin with. 20 of those became the 10 DF4 molecules. And the other 5 were left over. So getting that correct number, that was 1 point all or nothing for both numbers. All right, now for this part of the question, for other diatomic molecules, the student finds the diagram below, which shows the potential energy of 2 nitrogen atoms versus the distance between their nuclei, and the student incorrectly sketches the potential energy curve for 2 fluorine atoms, shown by the dotted line. So explain the error with the student sketch for F2. So triple bonds are stronger, but also shorter than double or single bonds. So single bonds need to be weaker and longer. So the student understood that the potential energy is much less, like the magnitude of the potential energy is much less because it is a weaker bond, but they should have drawn it coming out like way over here, okay, because the internuclear distance is going to be much greater because it's a longer bond. And of course, my drawing's not great, but the error is that the fluorine bond should be longer, have a greater internuclear distance than the nitrogen bond. And that was just 1 point. Okay, let's look at a different free response question. We have the decomposition reaction for N2O5, and they give you the rate law. So whenever you see something like this, I usually annotate. I can tell it's first order already because of the exponent of 1. And then, so we've got a sample of pure N2O5 placed in an evacuated container, allowed to decompose at a constant temperature. It's measured over time, and the measurements are recorded. Determine the value of the rate constant K and include units. The easiest way to do this, I think, is using the half-life equation. Because it's a first-order reaction, we know that the half-life equation is 0.693 over K. And so the time it takes for 1/2 of the substance to react. So if I'm starting at 0.16, half of that is 0.08. So the time it takes to do that is 1.67 hours. If I go ahead and solve for K, I get K is equal to 0.415. And then the unit here is inverse hours. It's hard to read. And that's because I went ahead and I kept the time in hours. And when I rearrange the equation, the hours winds up on the bottom, so that's why I get inverse hours. You could also write it, of course, 1 over hour if you prefer. You could have changed it into minutes or seconds first and then did it, but you'd get a different magnitude here. So this is probably the easiest way to do this question. You could have used an integrated rate law, but I think that's more difficult. Always be on the lookout when you have first order. Half-life is a nice, easy shortcut for a lot of these. This one was actually 2 points. One for getting the correct value of the rate constant, and the other one for getting the correct unit. So you could have just gotten the correct unit, knowing that it was first order. You don't include molarity in the unit for the rate constant for first order reactions, so you would just do the inverse time. Okay, so for this one, they give us the 3-step mechanism, and they want us to determine which one's the rate determining step. So let's look at the rate law that they gave us in the previous part was rate equals k n205, and it was first order. So if the first step was the rate determining step, then you have just one n205, which is consistent. If I said that the second step was the rate determining step, NO3 would cancel. And the NO2 would also cancel. So you could say that step 2 is the rate determining step as well. Because those things cancel out. They're intermediates. Now, if you were to check the third step of the reaction, the NO2 would cancel, NO3 would cancel, NO would cancel. I think that's it. So you'd wind up with 2 N2O5, which is not consistent. So step 3 could not be the rate determining step. It has to be step 1 or step 2. As long as you said one of those two and justified it in terms of the rate law having just one of those N2O5s present, you got the 1 point. Okay, so for part C, if this experiment was repeated at the same temperature, but with twice the initial concentration of N2O5, would the value of K increase, decrease, or remain the same? K would stay the same, and the K is only going to change when you're at different temperatures. If you use twice the amount of N2O5, your rate will double for sure, but K stays the same at any given temperature. So that is just 1 point for C. Okay, for this multiple choice question, they give us 3 steps in a mechanism, and they want you to find the products of the overall catalyzed reaction. So anything that is a product and then a reactant is an intermediate, so Mn3 plus is an intermediate, Mn4 plus is an intermediate. Anything that starts out as a reactant and then a product is a catalyst, so Mn2 plus is a catalyst. So the things that we have left over that we haven't canceled out, we have our reactants, and then our products, the Ce3 plus and the Tl3 plus. So those are the 2 products, so it's B. Now this is a half-life equation or half-life question. It says if 87.5% of a sample decays in 24 days, what is the half-life? So you could do this a couple different ways. The easiest way, I think, is to think about how much is remaining. So if you have 100% to start out with, and we reacted 87.5%, we're left with 12.5%. That's how much is remaining. Now, if we think about it in terms of half-life, you're cutting it in half each time. So in order to get down to 12.5 from 100, it had to undergo 3 half-lives. And each of those half-lives for nuclear decay is the same amount of time. And so if it's 24 days total, each one must be 8 days. And that is the half-life. So for this question, they give us an experiment, or 2 different trials of an experiment with different concentrations of X and Y, and then you're measuring the rate of formation of Z. It tells us if the reaction was first order with respect to X, so for our rate law, it would be X like this, and then second order with respect to Y, like that. And then they want you to find the unknown rate in terms of R for the first one. So what you could do for this, you could plug in the values and find K, solve for K. So if in the first experiment rate is R, K we don't know, X is 0.4, Y is 0.1, and we're going to square that. So if I were to solve, I get 0.004, and then I move it over, so K is equal to R over 0.004. Now what I can do is plug in to find my unknown. Well, I'm going to say that the unknown rate is equal to K. K is the same because it's the same temperature, which is R over 0.004. X is now 0.2. Y is now also 0.2 squared. So I can simplify this to R over 0.004 times 0.008, and you get 2R. I think that's probably the easiest way to solve for that because we know that K stays the same, so they're at the same temperatures. Okay, so we have a different reaction, and this time 2 separate trials were carried out using calcium carbonate samples of the same mass. One sample had a single piece, and one sample had many small pieces. So this is a collision theory question. The more pieces you have, the more surface area, and therefore the more collisions are possible. Now we have a loss of mass as a function of time for both trials, and which one represents the reaction with small pieces. Well, it's going to be Y, because this slope here is greater. It's going to reach kind of the limiting factor for the reaction faster, right? We're going to run out of calcium carbonate to react faster because those smaller pieces allow for more collisions to happen very quickly. So D is the better answer. This answer choice C is not a good answer. It says the reaction proceeded at a non-uniform rate. Well, yeah, but so does X. X also proceeds at a non-uniform rate. If it was a uniform rate, you'd have the same slope all the way through. So that is not a true statement. So D is the better answer choice. And our last multiple choice question for this unit, we have an oxidation of iodide ions according to the reaction above, and then they give you the experimental rate law. Everything is first order. That's nice. According to the rate law, an increase in the concentration of hydronium ions has what effect on the reaction? So if I increase the hydronium ions, that's going to increase the rate of the reaction, yes. It's not going to decrease it. It's not going to change the value of our equilibrium constant. So this is a Unit 7 kind of application here. Equilibrium constants and rate constants only change when there's a new temperature. So those are not good answer choices because the temperature is the same. Neither the rate nor the value of the equilibrium constant is changed. Well, we know that's not true because if we increase a concentration, it's also going to increase the rate due to more collisions. So A is the best answer choice there.